This is your lesson on variation problems found in Glencoe 9-4. We're going to start off with example number 1 where we're looking at some direct variation problems. If y varies directly as x, that means y is equal to kx. And y is 12 when x is negative 3. Find y when x is equal to 16. You're going to notice that my approach is different than the textbook's approach, but both are perfectly acceptable. I'm going to plug in my given coordinates, so my y value of 12. I don't know my k value, and I do know my x value of negative 3. I'm going to divide both sides by negative 3, so 12 divided by negative 3 gets me a k value of negative 4. So now I have my linear equation of y equals negative 4x. So I'm to find y when I have an x value of 16. So y is just going to be equal to negative 4 multiplied by 16, which is just negative 64. All right, so that's direct variation. Now we're going to take a look at some joint variation problem. All right, so suppose y varies jointly as x and z. That means our joint variation equation is y equals k times xz. Okay, I'm going to take this problem as the same approach as I did the last problem. Okay, so find y when x is 8 and z is 3. If you're given y is 16, don't know my k, when z is 2 and x is 5. Okay, so I plug those in. So 16 is equal to 10k. Divide both sides by 10. So 16 tenths, that's going to simplify. Both numbers have 2 go into it, so 8 fifths is equal to my k. I see the textbook is starting to use a decimal here, so that's perfectly acceptable here too. So it's going to be 1.6 is our k value. So my equation is y equals 1.6 xz. I'm now going to plug in the given x and z values that I was told to use in order to solve for my y value. So when I multiply 1.6 times 8 times 3, that's going to get me a y value of 38.4, and there you have it. There is our joint variation problem. Alright, we're on to our last two examples for variation. So the third type of variation we're exposed to is inverse variation. So we're given the equation if r varies inversely as t, that means we're going to use r is equal to k divided by t. And r is 18 when t is negative 3. And then I'm going to find r when t is equal to negative 11. So I'm going to take this equation and solve for k. Multiply both sides by negative 3 over 1. So 18 times negative 3, that's going to get me negative 54 is equal to my k value here. Alright, so now I have my equation. R is equal to negative 54 over t. Find r when t is equal to negative 11. So negative 54 divided by negative 11. Negative divided by negative is a positive. So r is equal to 54/11. Textbook says you can give it to it as a mixed number. I will leave it as an improper fraction. You can also give me a decimal answer. Alright, so we're going to take our last example, and we're going to stick to the way that the textbook is solving it, just to help get you a little frame of reference as to why and how the textbook is solving it the way it is, well, it's being solved. So, inverse variation can be looked at in multiple ways. One of the ways that your textbook also uses x times y is equal to k. That's why you can set proportions equal to one another. And so what the relationship that your textbook is going to be using for this problem actually is the fact that, so the distance from Mercury multiplied by the diameter from Mercury is going to be equal to the diameter from Earth multiplied by the distance from Earth, okay? This relationship will be the same, okay? That's what they're saying here. But what they do to break it up is they're going to divide away both sides by this diameter portion here, okay? So that's why they end up with this equation of distance from Mercury over diameter from Earth is equal to the distance from Earth over the diameter of Mercury. Okay, now let me zoom out here a little bit to give myself a little bit more room. We are just going to basically plug in some information now, okay? So the other thing that your textbook makes a nice little leap towards the ability to use is they make this assumption that the diameter, the apparent diameter from Earth, because Mercury is just so close, they're going to let it just be 1 unit, okay? It's kind of an assumption, and that's why they clearly state this assumption here, okay? And we don't know this value here. This is this value of diameter of m. He is just going to be our variable m. So the distance for Mercury, this is going to be our 36 million miles. We're going to let it be over 1 unit for whatever our diameter is going to be. Distance from Earth, that's that 93 million number. And we divide that by m, okay? So what we're really doing here is we're solving for m. So what essentially you do here is cross multiply. Multiply both sides by m and then divide both sides by 36 million. So we're really going to have 93 million divided by 36 million. So if you want to solve this using scientific notation, you're more than welcome to. It's also pretty easy just to calculate in your calculator. Millions will divide away each other. So we're really just dealing with 93 divided by 36, which gets you 2.58, okay? All right, I'm going to put a little PSA out there for one other resource that I think would be helpful in understanding these problems here. Found on TestStream, but I'll also put it up here, is called Purple Math. If you simply just Google variation in Purple Math, you will find wonderful examples of real-world problems as well as other normal problems.